Hi, folks. So this is part two of the Module 10 demonstration video. In part one, we're talking about confirmatory factor analysis, and we explored a CFA model, confirmatory factor analysis model for the computer scale, all the questions that pertain to anxiety around computers on Andy Field's SAQ, Statistics Anxiety Questionnaire. And we looked at how to generate both standardized and unstandardized solutions, how to examine model fit, some of the parameter estimates, and also how to create a pretty cool path diagram. The actual models, of course, were created in Lavon, the Lavon package, and the SEM plot package is our means of creating those path diagrams. So now we're just going to try a CFA for a second scale, the friends subscale, just to give you experience with working with this whole process a second time. So there are a series of 5 questions, including question 23, which is the one that I added to the computer subscale that didn't fit very well, that pertain to what I call friends. And it's sort of peers or friends judging you or watching you do statistics. It's kind of a peer effect on this anxiety question. So those 5 items, 2, 9, 19, 22, and 23 pertain to this friends piece. So I'm going to create, again, a new CFA model. And the first thing you do is you create the model in text. So here, my latent variable is called friends. And it, again, is a function of using this special assignment operator in Lavon. It's going to be composed of questions 2, 9, 19, 22, and 23. And so I first can load that up into my memory here, run selected line. So there it is. And looking at the environment here, I have my first friends item and then my second friends item are both in there. And then next I can, sorry, I'm having some mouse issues. Okay, we're good. Here are my 3 models here. So next I can run this model. So I'm going to call this friends CFA model. So this is actually the results. And it's going to be a CFA based on the friends CFA text. And then my data set is the same. So run that. And then I'm going to get a summary of this, again, with fit statistics and standardized estimates. So here again, I've got 10 free parameters. That is the difference between the number of data points and the number of parameters being estimated. I have, let's see, I have a chi-square value of 44.608, 5 degrees of freedom. So that is still not statistically significant. Or it is statistically significant. We want it to be non-significant ideally. But again, this is a large sample. CFI is 0.96, which is good. TLI is a bit low at 0.92, although it's not terrible. And then my fit statistics here, RMSEA looks pretty good. The confidence interval does contain 0.05, and the p-value is non-significant. So that's pretty good too. So all in all, this looks like a pretty decent model, although it doesn't look like it's below 0.05. The RMSEA, although 0.06 is generally the cutoff. So this doesn't look too bad. And SRMR is not too bad, again, at 0.03. Here are my parameter estimates. These are my factor loadings. Again, the unstandardized estimates are in this column. We see we've used the marker method. We've fixed the loading or the slope of question 2 equal to 1. And then here are the factor loadings. Those look pretty good, although question 9's a bit larger. And then here are the standardized loadings. So 0.4, 0.5, 0.4, 0.5, and then 0.3. This is a bit low for item 23. You might consider just giving that one a look and seeing if it would belong in an additional model. But anyway, so that's just another example of running a CFA for another scale. And then again, we can use this SEM paths command to get a standardized estimates and a path diagram. Again, here are the items and here are the loadings. Here are the error variances down here. And this is the variance of the latent variable. Okay. So you might ask, okay, we did a scale for computers, a subscale. We did a subscale for friends. Can we combine all the elements, or at least most of the elements on this scale, into a combined model? And the answer is yes. You can run what's called a correlated factors model. And that is where you have a series of latent factors, of latent variables that are correlated with each other. So in this case, we're combining computers, which was the first one we looked at, with friends. And then we're adding this math component. This is the one that has to do with like standard deviations and central tendency and all that stuff. So what we're testing here is whether or not these items are best represented by a series of 3 correlated latent variables, one about computers, one about friends, and one about math. And notice I just put on a different line each latent variable. By default, the software knows that all latent variables need to be correlated with one another. So it's going to do that. And it's going to give us the combined model that we're looking for. Again, all of these things go within single quotation marks, and you just bump to a different line for each construct. One thing to note, you need to highlight the whole model in text to run it. You cannot run a model like this line by line, because the model itself extends onto multiple lines, and the software needs to capture all of that at once. So if you want to do this sort of line by line, I would highlight this whole portion and then say run selected lines. And that will load the correct model, which is right here, CFA 3-factor, into your environment. So then we can fit a model, CFA 3-factor model. Again, it's a CFA using the CFA 3-factor model specifications, the same data set. So we run that, run selected line. You can also do control enter is another trick for that. And then we'll get a summary and estimates of this correlated factors model. So here is our chi-square. Again, highly significant. That's common in a data set this large. CFI and TLI are not too bad. Ideally, we want those above 0.95, but above 0.90 will often be sufficient. RMSEA actually looks very good. It's 0.05 with a pretty tight confidence interval between 0.05 and 0.057. Ideally, we want this thing below 0.06, so that's great. And SRMR looks pretty good at 0.04. So this is a pretty well-fitting model. Here are the factor loadings. I, again, usually skip to the standardized and just sort of scan for items that are below 0.04 or 0.04. And really the only one that jumps out is the friends estimate, which we found when we looked at the friend scale by itself. The loading of item 23 is a bit low here. So again, you might consider if you want to change that. And then we have covariances. So this is new. We haven't had this before. But what we tested was a correlated factors model. And so we're actually testing at the same time we're building our latent variables. We're also testing the correlations between the latent variables. So this is pretty cool. It shows you the extent to which your different constructs are actually related to each other. So the raw estimates are here of those covariances. And the way you read this is, first of all, this is computers. And this double tilde sign is the sign for a covariance. So this is the covariance between computers and friends, this estimate right here. And this estimate right here is the covariance between computers and math, computers and friends, computers and math. And then this last covariance is the covariance between friends and math. Now, these are all unstandardized over here. So interpreting an unstandardized covariance is not very intuitive unless you really know the scale of the questions pretty well. And so if you go over here to STD all, This gives you the correlations, essentially the correlations between the latent factors, not the covariances, which are unstandardized, but the correlations. So the correlation between computers and friends is essentially minus 0.5. So what that tells you is someone with more anxiety about working with computers tends to have less anxiety about friends judging them, right? So if you're more anxious about this, you're going to be less anxious about that. Someone, on the other hand, who is more anxious about friends judging them is also going to be less anxious about the computer piece. So there's kind of an interesting negative relationship there. Computers and math is positively correlated. So if one is high, the other is likely to be high. And friends and math is similarly negatively correlated, just like computers and friends. So that's a cool little addition you get with this piece. You're able to sort of look at the correlations between all these things. And then, of course, we get the variances of each item. Higher here, right, suggests that more of the variation in that item is unexplained. And less of the variation in the item is actually contributing to the latent factor. So it's more unique, I guess, is one way to think about that. We can visualize this again with the SEM paths function. And I always think these correlated models look cool. So here are all of our items running along the bottom. And there we see all of the covariances, the error covariances, or error variances. And then we have all of our item weights here. Here's the computers factor, here's friends, and here's math. And then this represents those covariances. So here's the covariance between computers and friends, here's friends and math. And then this line here is the covariance between computers and math. And then we have the variances of the latent variables, which in this case are fixed at 1 because we're looking at standardized estimates. So that's pretty cool. I don't know. I always think that path diagrams are kind of neat. They represent a lot of pretty cool things. Okay, so let's test a couple other things. So what if we wanted to combine the entire scale all together? So what if we wanted to say, okay, let's take all 23 items from the Andy Field scale and put them together. What's interesting about this is if we were to calculate an alpha based on this, the alpha for this scale is actually probably pretty high because by definition, alpha increases as you add items, even if the items you're adding are not all that correlated with a common factor. Chromebox alpha by definition is going to go up. It's a little bit like R squared in that way. So a factor like this is likely to have a high reliability, but it may not be all that internally consistent in terms of should we consider all of these things as equally contributing to the same latent factor? And that's what we're testing here. So this is CFA all one factor. So I call this thing ANX for anxiety, and it is composed of all 23 items, 1, 2, 3, R, 4, 5, 6, all the way to 23. And then I just fit a model based on that equation. And again, CFA for all one factor, and then a summary using the standardized solution. So again, this is the one factor, and chi-square here is pretty high, 4,000 points, 200 degrees of freedom. When we get into this, notice the fit is very, very poor. CFI is 0.79, TLI is 0.77. Those are well below the threshold, any threshold that we might consider for good model fit. RMSEA is not terrible, but it's still pretty high. It's above 0.06 consistently. And SRMR is slightly above 0.06 as well. So in terms of model fit, what that's telling us is a one-factor model probably does not fit that underlying data all that well. The underlying data probably are more likely a sort of a series of correlated factors or something similar. So this is an area in which CFA is really an extension of, for example, looking at something like Chromebox Alpha or Omega, because it allows you to really sort of dive in and explore some of these alternative setups for the way different factors can operate. And when we get into this, we notice right away, I mean, whether we look at these standardized or unstandardized, the loadings are sort of all over the place, right? So there are some negative loadings, item 2, item 9, 19, 22, 23, and these aren't reverse coded items either, right? They're all sort of coded in the same valence, so that's weird. We also have a lot of low loadings, 0.2, 0.2, 0.1 even. So the factor loadings here are also not great. So long story short, we probably don't want to treat this as a like a unidimensional thing, right? And call it anxiety and use it as a measure. We probably are much better off kind of splitting it off into subscales and just looking at those correlated subscales as a way to kind of look at this. This is just a picture of that model. Again, one latent variable called anxiety, all 23 items contributing to it. We can make this a little bit bigger if you click the window here. I have a pretty big monitor right now, so it'll separate. Bless me. It'll separate out all these components pretty well. But this is just what it looks like. This is the unidimensional one-factor model for anxiety using all the items, although this is, not a good fit based on what we found about the data. All right, so the last trick we're going to talk about this week are modification indices. And those are what I call Pandora's box a little bit. So, there's this story about Pandora and sort of opening the box, and, you think it might be a good thing, but it actually ends up getting you into more trouble than not. And that's also the case with modification indices. What modification indices tell you essentially are the modifications that you could make to your existing model that would improve model fit. And so it sort of gives you a laundry list of all the ways in which you could improve the fit of your model. And it also tells you what you can, sort of the extent to which each modification will improve your model, which is really interesting. Now, a word of caution with these. Often what happens when you look at modification indices is you run the risk of doing something called overfitting, which means you actually are tuning your model too much to the specific characteristics of your data and sample. And in doing so, you're reducing the generalizability of your model in other samples. So if we fit a model that is very specific to the data we've collected, by definition, if we go and collect new data, that model is not going to perform as well. And so another word for this is the bias variance trade-off. This is another thing that gets talked about. So is very specific models don't perform well in larger samples. And so, or in new samples, I should say. And so that's where Pandora's box can be really, really tricky, but I'll show you what they are and how they work. So the command is really straightforward. It's from Levon, modification indices, and then you list your model. And then I like this sort function because this sorts them in order of the most influential to the least. And then I recommend specifying a minimum value because, like I said, this will be a laundry list of little tweaks that you can make to your model, but you really only want to see the ones that are big, that cause big changes in model fit. And so 3 is sort of the cutoff for a 1 degree of freedom change in a chi-square. And so that's typically the cutoff that I like to use. So we run these and we get our modifications. So there's actually 17 rows. So there's 17 of these modifications that are recommended. So the way these work, they're sorted from the most influential to the least influential. And the way you read this, left-hand side is LHS, OP is operator, and RHS is right-hand side. And so all of these double tilde rows, these are suggesting error covariances. So what an error covariance is it means that the error term that we estimate, the variance of one item, is specifically correlated with the variance of another. In this case, if we were to specifically correlate the error of question 6 with the error in question 12, that will result in an improvement of 108 chi-square points. Now, is that a lot? Not necessarily in this case, because I forget how many chi-square points we're looking at. I think we're in the 400s for this model. This is the computer's CFA1 model, I should say too. This is not the full model with all the items. This is the model up here. Let me scroll up. This is computer CFA1. So we're just looking at the 8 items that include computers. And we get 17 possible modifications that we can make. So this one actually will give us quite a bump. Now, and here are some others. So if we correlate items 6 and 7, it'll improve by 45 points, 15 and 18, so on and so forth. And it looks like all of these are just item covariances, which are often recommended. In this case, now, if you have longitudinal data where you've collected waves over time, it is recommended that you correlate an item in one wave with an item in another wave. Correlation across time is something else. But here in a cross-sectional data set, you really have to be careful justifying these error covariances because, again, you run the risk of overfitting. You might be really just zoning in on the sort of quirks or eccentricities of your sample, and that can lead to problems when this tries to generalize down the line. So let's say we wanted to do this, though. I can show you how to do this. So let's say we wanted to make this modification. I'm going to call this computer CFA3. So here's the original computers model. And then I just bump down to a new line, and using that double tilde sign, that error covariance, I correlate item 6 with item 12. And in doing so, I'm actually doing what's recommended right here at the top. So this should significantly improve the fit of my model. Then I run this, and I could add other additional, I could bump down a line and add additional changes if I wanted to, additional restrictions. So let's run this and see how it looks. And sure enough, the fit, let's ballpark this. So let's look at the fit of computer CFA1. So here's the original computer CFA1. Our chi-square was 250 points. RMSEA was around 0.7, SRMR 0.03. Oh yeah, I need the standardized estimates here. Oh, I guess I didn't get, did I? Yeah, computer CFA1. Yeah, so it's CFI was 0.96, TLI was 0.94, and then 0.07 and 0.03. So I'm just going to scroll down to the bottom and compare. Just do a quick comparison. So this is the modified model. Chi-square is 136. So significant improvement in the chi-square. It's lower. CFI TLI 0.98, 0.97. So both of those are up. RMSEA down 0.049. It was 0.07. And SRMR is lower too. And here is that specific covariance that I specified between these two items. So it does absolutely improve the model fit. I mean, we know it would, because that's what the modification indices were actually telling us. And here's the model. And you can see the difference is, see this little arrow, this curve right here, that is the error covariance between items 6 and 12. Now, again, in this case, it's probably not a good idea to do this. We're capitalizing on chance here and specifying something that will likely not generalize. But it is interesting to see how those little small modifications can make such a big difference in the overall fit of the model. So those are modification indices. So just to recap, we've covered quite a bit here. In the second half, we talked about how to put together correlated factors model. So we estimated the friend scale, and then we did computers, friends, and math all together. And then we talked about modification indices. We said what happens if we just dump all these items in under one latent variable, and that didn't work very well. And then we tested modification indices, looking at those, and also testing a modified model. So you've got some of the basic tools now to do some CFA of your own. and explore some of the dimensions of how a scale might be functioning. So hopefully you find that useful, and we'll talk soon.